We touched on this in the video on resonance, but I want to devote an entire video to aromatic compounds. Aromatic compounds. And one of the big mysteries in chemistry is why they were named aromatic compounds, because it clearly comes from the word aroma. So one would think maybe all of these compounds smell good or smell bad or don't smell at all, but it actually turns out that a lot of them don't even smell at all. So it's a little bit of a mystery. Some people think that they have some relation. The gentleman who named them saw that they had some chemical relation to things that did smell, so that he named them aromatic compounds. So it is a bit of a mystery. In general, the most common aromatic compound, and really this is like 99% of the time what you're going to see in chemistry class as an aromatic compound, is either benzene or a molecule derived from benzene. And let me draw benzene right here. So benzene is normally drawn like this. Let me draw. So it's a 6-carbon ring, and it has 3 double bonds. It has 3 double bonds like that. And we learned in the resonance video that this isn't actually the only configuration for benzene. It could just as likely be in this configuration. That this electron up here might move there, this electron might move over there, and then this electron might move over there. So let me clear that up just so you don't make it too confusing. So it could just as likely be in this configuration. It could just as likely be in this configuration right here, where the double bonds are on the other bonds that aren't double bonded over here. So it could just as easily be over there. And we learned in the resonance video that the reality is it's actually in between. And sometimes it's drawn like this, as going back and forth between these configurations. But the reality, and you'll sometimes see it drawn like this. You'll sometimes see it drawn like this, which is a circle in between, in the middle of the hexane ring, I guess you could say, or the benzene ring, which is showing that the electrons, those pi electrons, those electrons that form the double bond, are actually they're going back and forth between this. They're just spreading around the entire ring. And what makes aromatic compounds interesting is because these pi electrons can spread around the entire ring, that it's actually a much more stable configuration, or a much more stable molecule than what you would predict if you just looked at one of these two configurations. And another way that it's often drawn looks something like this. Another way, and I'm just doing it in yellow just to have something in a different color. Sometimes you'll just see this, that it's someplace in between that and that. So you'll have a dotted line there, dotted line, dotted line, dotted line, dotted line, dotted line. This is the most common kind of shorthand for showing both benzene and for showing that it's experiencing this resonance, that you have this conjugated system of pi electrons. And I'll help you visualize that in a second. But you also might see it something like this, that it can go back and forth and everything in between these two configurations. Now, just to visualize what's going on, because you'll see sometimes here people talk about conjugated system of pi electrons, I want to actually help a little bit more of visualizing what the molecule might look like in 3 dimensions. What it might look like in 3 dimensions. So that is the 6-carbon ring right there. So it's carbon, 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 carbon. And then each of these carbons is bonded to 3 other atoms. It's bonded to 2 carbons, and it's also bonded to a hydrogen. So let me draw the hydrogens here. So they're also bonded to hydrogen. So this one will have a hydrogen over here. This will have a hydrogen over here. That will have a hydrogen over there. That one has a hydrogen over there. Hydrogen and hydrogen right over there. So if we talk about hybridization, we have 3 hybridized orbitals. This is sp2 hybridization. And each of these have a leftover pi orbital that has not been hybridized. It's not directly bound to, or that does not have a sigma bond to another atom. So you have these pi orbitals, and these pi orbitals look like these dumbbells. So you have a pi orbital over here. You have a pi orbital over here. Pi orbital over here, pi orbital over there. You have another pi orbital over there, pi orbital, and pi orbital. And pi orbital, I drew them like this, because if I drew them bigger than that, the diagram would get messy. But in general, whenever you have double bonds, like this double bond, let's say that this carbon let me change color so we know what we're focused on. So let's say this sigma bond right over there. Let's say that that sigma bond right over there is this sigma bond. Actually, let me do another one just so it's easier to see. Let's say that this sigma bond right over here is this sigma bond between these two carbons. This double bond, the double bond in blue, this one, or in purple right over there, that's due to these overlapping pi orbitals. That carbon's pi orbitals and that carbon's pi orbitals overlapping. I haven't drawn them overlapping, but, well, actually, an electron can really show up. It's all probabilistic anyway, but I could draw them big enough, they would overlap, and these electrons would form that extra pi bond. What happens in a conjugated system of pi electrons, let me write that down since it's a very fancy word. Conjugated system of pi, let me write, pi electrons. Conjugated system of pi electrons. These guys, as we see, they could be bonded with each other. These guys could overlap. So there could be an overlap going on over here. Or we could flip into this configuration where this guy would overlap with this guy over here. And the reality is that these pi electrons will actually be able to float around the ring. They'd actually be able to float around all of these pi orbitals right over there. They'd actually be able to float around the ring. So that's what people are really talking about when they talk about aromatic compounds or aromaticity, that because of this, this is a more stable compound. And the most typical one you're going to see is a 6-carbon chain with 3 double bonds, benzene, or things derived from them. But there actually are more general ones. In general, you're going to see anything that has 4n plus 2 pi electrons in a cycle is going to have aromaticity, or it's going to be an aromatic compound. So let's just confirm this actually makes it. So each of these guys over here have 1 pi electron. Even though this looks like kind of 2 bonds, remember this is one pi orbital right over here, and you have 1 electron that's going to be in this entire pi orbital. So this has 1 pi electron, 2, 3, 4, 5, 6. Another way to think about it, each of these double bonds involves 2 pi electrons. So 1, 2, 3, 4, 5, 6. So that follows what is called Huckel's rule. Huckel's rule. I think there's 2 dots above the U. Huckel's rule, maybe? That follows Huckel's rule, because if you set n is equal to 1, 4 times 1 is 4 plus 2 is 6. So 6 pi electrons work. If n was 2, you'd have 4 times 2 plus 2, which is 10. So if you had 10 pi electrons, it would also work. So a molecule that looks like this, let me see if I can draw it. A molecule that looks like this would also work. So if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and then you had 5 double bonds. So 1, 2, 3, 4, 5, just like that. And you can imagine these guys could flip around, but this would also be an aromatic compound. This has 10 pi electrons. Each of the carbons have a pi electron, or you could count the pi electrons on each end of these pi bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, this is one thing that I always wonder. It's like, okay, it worked with 6, it worked with 10, but what about 8? It seems like with 8, maybe these electrons, these double bonds could flip around just as easily. So what if I had, or even 4, what if I had a molecule that looked like this? What if I had a molecule that looked like this? Or a molecule that looked like a stop sign? So 1, 2, 3, 4, 5, 6, 7, 8. That had double bonds that alternated like this. You might say, hey, maybe those also are aromatic compounds. Those also experience aromaticity, because couldn't this guy jump around here and then that guy over there, and the electrons cycle around, or this guy jump over, these electrons move there, those move there, those move there, and those move there. And it turns out that in these compounds, it's actually the electrons do not, the pi electrons do not stabilize the system. That this is actually less stable than if it was not in a cycle. So actually, this is these right here that don't follow the 4n plus 2. So 4n plus 2, you're talking about 6, 10, 14 pi electrons, which usually means 14 carbons or 10 carbons or 6 carbons. The ones that don't follow them but are still cyclical and still have these alternating bonds, these are called anti-aromatic. These are anti-aromatic, and are actually very unstable. These are very, very unstable and are more likely to break into a non-cycle. Anyway, hopefully you found that vaguely useful.